Hi, welcome back. This video is really the first video in the second half of our course. And in the second half of our course, we're going to use Fourier analysis quite a bit. And so in this video, I want to show you a little bit, give you a little bit of history on Fourier, and then also motivate the use of Fourier analysis for our purposes in signals and systems. Okay, let me give you a little bit of history of what it was that Fourier was working on. And then I'm going to get to these 2 points in a second. Now, Fourier was a mechanical engineer, and he was working on what was called the heat plate equation. And the heat plate equation goes like this. Given a heat source, x of t, so the heat source varies with time, can you find the temperature at some point y of t, given properties of the system, that is the heat plate? That's it, right? So that's exactly what we do. We have inputs and we have a system, and then we try to find the output. So for the heat plate equation, Fourier knew the solution when x was sinusoidal. This was new. This was known before Fourier, that when x is a sinusoid, which means sine, cosine, exponential, complex, then you could find you could solve the equation. But that's not very practical, because how often in real life do you have a heat source that's just oscillating? Probably never. Fourier also knew that this equation was linear. The heat plate equation, that is, was a linear equation. So that means that if you could express other signals that are not sinusoidal, maybe like this one, if you could express them as a sum of sinusoids, then maybe this signal is some sinusoid plus another sinusoid plus another sinusoid, then you could find the solution here and find the solution here separately, and this separately, this sinusoid, and then add them all up, because that's linearity, and then thus you would have the solution due to this composite signal x of t. So Fourier began to ask the question, what signals can I construct by just adding up a bunch of sinusoids? And the answer is an astonishingly amazing answer, and that is that x of t, or any x of t, any signal, can be written as a sum of sinusoids. So that kind of brings up this first point here. It turns out that complex exponentials, so we'll just write it like this, e to the st, where s is a complex constant. E to the st can be used to construct a broad, not borad, whoops, I got a typo there, a broad and useful class of signals. By adding a bunch of complex exponentials together, we can construct any signal, like a square wave, for example, or a square pulse. We can just add up a bunch of oscillations. It's amazing, and we can get this. Now, this would not be very useful to us if e to the st was not convenient when analyzing LTI systems. So this is the second point. Well, let's see what we get out of an LTI system when we put in a little complex exponential. Well, what do we get out? We get out the convolution of the input with the impulse response. Okay, so what? Well, I can use the property of exponents to break this down, and I can bring out e to the st because it's independent of tau. So this gives me e to the negative s tau now, inside times h of tau. And this integral is a number. Given s, right? Given the input s, I integrate with respect to tau, plug in the bounds, and that I get a number that depends on s. So we're going to call that number capital H and show its dependency on s like this. So I've got a constant, possibly complex, times what I started with, right? I put in e to the st, I get out e to the st. That's amazing. That's amazing. I put in this signal, I get out the same signal, scaled by a constant. So this is very convenient for us. These little complex exponentials, these sinusoids, are very convenient because I put it in, I get it out, right? Think about taking a calculus test, and maybe your entire test was like, take the derivative of this function. Oh, we like that because when we take the derivative of e to the ax, we get back e to the ax multiplied by a constant. That's nice, right? That's convenient. I think you will agree. So we start to ask the question, well, what types of signals can I get by adding a bunch of complex exponentials? For example, maybe adding 3 complex exponentials, each with their own amplitudes, a1, a2, a3, and their own complex constant there, s1, s2, s3. Well, what do I get out? Well, because the system is linear, I can consider each piece separately, and what I get is the same thing out multiplied by that constant. We're not going to say too much about that constant yet, but just in general, this is what we would get out, right? We love this. We love this idea. Oh, wow, I can get the output very quickly, right? No convolutions necessary here. Because I know that I put this in, I'm going to get all those things out multiplied by this constant that depends on S1, S2, and S3. Wow, we love that. That's exactly what Fourier was doing. What sort of signals can we construct with these complex exponentials? It turns out every signal we can construct like that. All right, so this is a huge thing for us, and we're going to investigate this in quite a bit of detail. And so the first thing we need to do is we need to figure out how we can take a signal and decompose it into these sinusoids, right? I already mentioned that we can take, or that a square pulse can be written as a sum of sinusoids. So how do we go from a signal and get its constituents? How do we get its recipe, right? And this is the Fourier series. So we'll say more about that in the next video.